Today I've got a nice number theory problem involving an exponential equation. And this one comes from a Taiwanese math Olympiad from the year 2000. So our goal is to find all natural numbers m and n satisfying this equation. We have n to the power of m squared is equal to m to the power of n plus 2. Okay, so let's start our solution by noticing that if m is equal to 1, then that means the entire right-hand side of this equation is 1, because 1 to any power is 1. But that means that n to the m squared is equal to 1. But then since we're working over natural numbers, the only natural number that exponentiates to 1 is the number 1. So we get that n is equal to 1. And in fact, you can check that if m and n are both 1, that is indeed a solution. So let's maybe put that here. Our first solution to this equation is the solution m equals n equals 1. Okay, now let's maybe dually notice that if n is equal to 1, then the entire left-hand side is equal to 1, which means the right-hand side is also equal to 1. So we have m to the n plus 2 is 1. But again, since we're working over natural numbers, we get that m is also 1. So what this tells us is that if one of them is the number 1, then both of them are the number 1. So that really tells us that from here we should look at solutions where neither are 1. In other words, when they are both bigger than 1. So let's put that here. So now we assume that m and n are both strictly bigger than 1. But if they're strictly bigger than 1, then that means they're composite, and in fact they're divisible by a prime. Notice they're not divisible by a prime if they're equal to 1, so that's why it's important to break these into cases. So let's take a prime p dividing, let's see, maybe which one do we want to start with? Maybe dividing m. Okay, but now if p divides m, then that means p divides the entire right-hand side. But that means p divides the left-hand side as well. So that means we have p divides n to the m squared. But if p divides something with a base of n, then that means that p must divide n. So we have p is equal to, p divides n. Okay, so now let's also notice very, very similarly, we have if p divides n, then that means that p divides m. Now putting these two facts together, we have that m and n have the same prime factors, potentially with different exponents though. So let's write that here. So m and n have the same prime factors. And what does that mean? Well, that means that we can write m and n with their prime factorization, again, with the same prime factors. So we have m is equal to p1 to some power a1 times p2 to some power a2, all the way up to, I'll call it pr to some power ar. And then likewise, n can be written as p1 to the b1 times p2 to the b2, all the way up to pr to the br. And the important thing is we can take all of these exponents to be bigger than 1. And that's again because they have the same prime factors. So let's point that out here. So where ak and bk are all natural numbers. And now let's get our original equation on the board because we're about to extract something from it. Maybe what I'll do is I'll expand n out and m out on either side. So that's going to give me p1 to the b1 multiplied all the way up to pr to the br, and then that is raised to the m squared power. And then we have, let's see, p1 to the a1 all the way up to pr to the ar, and that's raised to the n plus 2 power. Great. And then from here, what we'll do is extract the exponent of pk for an arbitrary k here. So let's maybe write that here. We're going to extract exponent of p to the k. And this extraction is a well-defined operation because we're talking about a prime here. Okay, so over here on the left-hand side, that will be equal to b to the k times m squared. Just using exponent rules to distribute that m squared over all of those things. And then over here on the right-hand side, that will be ak times n plus 2. But let's maybe rewrite this just a tad. And notice that that means we can write bk as n plus 2 over m squared times ak. And since all of these were chosen arbitrarily by taking the exponent of p to the k, we know this must be true for all k between 1 and r. Okay, but now we've got a rational number times ak is equal to bk, so we might as well take this rational number and put it in lowest terms. That'll like simplify our calculation. And maybe we'll use the lowest terms to be a over b, where the GCD of a and b is equal to 1. Okay, so now rewriting this, what do we see? Well, we'll see that b times bk is equal to a times ak, and this has got to be true for all k between 1 and r, where the GCD of a and b is equal to 1. So let's maybe write that as well, just so that we know. GCD of a and b is equal to 1 because we reduced that to lowest terms. Okay, so let's gather that information at the top and then we'll move on. So this is where we ended up at the end of the last board. We had m and n had the same prime factors and they factored as follows. Then we were able to write an association of these exponents with a times a to the k equals b times b to the k, and the GCD of a and b was 1. Oh, but let's notice that the left-hand side is a multiple of a. That means the right-hand side is a multiple of a, but b cannot be a multiple of a, which means bk is a multiple of a. So that means we can write bk as a times, let's call it ck. And here, ck is a natural number, and this is occurring for all k between 1 and r. But now we can thread this back into our original equation. Well, maybe not our original equation, but that equation that we have up here. And we'll have a times ak is equal to, let's see, it's a times b times ck. Okay, and then we can cancel the a's from both sides of the equation, and we see that ak is equal to b times ck. And this is true for all k between 1 and r. But let's now put that back into our m and n expression. And we'll have m is now equal to, let's see, it'll be p1 to the b times c1 all the way up to pr to the b times cr. And then we'll have n is equal to p1 to the a times c1 from this right here all the way up to pr to the a times cr. Okay, nice. But I think it's pretty clear what we can do now. We can rewrite this as p1 to the c1 all the way up to pr to the cr, all raised to the b power. And then down here, we can write this as p1 to the c1 all the way up to pr to the cr, all raised to the a power. So in other words, m and n are exponents of the same number. This number right here, which is the product p1 to the c1 up to pr to the cr. Let's maybe go ahead and give that number a name. Maybe we'll call it c. So we have this is equal to c to the b, and then this is equal to c to the a. So just to reiterate, now we have m as c to the b, and we have n as c to the a. So now let's loop that into our original equation and see what that leaves us with. So we'll have n right here, which, like I said, was c to the a, and then that's raised to the m squared power, but let's notice that m squared will be c to the 2b. So we've got this is raised to the c to the 2b power. Okay, and then we need that to be equal to m to the power n plus 2. So m is c to the b, and then we raise that to the n plus 2 power, but that's going to be to the c to the a plus 2 power. Okay, so now let's simplify that using exponent rules. That's going to give us c to the power a times c to the 2b. That's on the left-hand side. And on the right-hand side, we'll have that is c to the power b times c to the a plus 2 times b. And then from here, we can just extract the exponent from c, and that's going to give us something that hopefully is slightly simpler. We have a times c to the 2b is equal to b times c to the a plus 2 times b. Okay, let's bring that up and then we'll work towards the end. Okay, so this is what we ended with, and now let's go from there. So let's notice that if we have a prime p that divides c, but if it divides c, then it divides m and n, so it's one of these right here. And let's suppose that we have p to be bigger than or equal to 3. So we actually want to show that this is problematic. So just to reiterate where we are, we're assuming that we've got a prime which is bigger than or equal to 3 dividing both m and n, in other words, dividing c. But now let's see where our contradiction comes from. So notice that 2b is most definitely bigger than b, which is bigger than or equal to p to the power, well, it's the exponent of p inside of b. And there's some notation for that. So we used that before without notation, but the notation for that is nu sub p of b. And we know that this is bigger than or equal to because this is just focusing on one prime factor of b. I guess we should point out here that since p divides c, and we have this equation is satisfied, that also implies that p divides b. So p is a prime factor of b. But since p is bigger than or equal to 3, then something in the exponent of p is always going to be bigger than or equal to this something that we have. So we have this is nu p of b. Okay, so we have this inequality right here. 2b is strictly bigger than nu p of b. And that's most definitely true. But now let's take our equation right here and show that that will actually lead to a contradiction. And we'll do that by applying nu p to both sides of this. So applying nu p here will actually just give us nu p of c to the power 2b. And that's because a does not contain a factor of p. That's because a and b are relatively prime. So since p divides b, we know p does not divide a. Okay, and then over here we'll have, let's see, that will be nu p of b plus nu p of c to the a power. And finally over here, since p does not divide 2, we have just nu p of b. So we have something that's starting to look like this. But notice by exponent rules, the power of the prime here will be 2b times nu p of c. So again, that's by exponent rules. So we have 2b and then we'll have nu p of c equals nu p of b plus nu p of b, so that'll be 2 nu p of b. And then here you can bring this a down. We have a nu p of c, like that. But now here we can drop some terms and pick up an inequality. So notice we'll have 2b times nu p of c is in fact less than or equal to nu p of b. So again, like I said, we dropped some terms and got an inequality. But now we can drop this nu p of c and push it further this way, and we'll have 2b. So in the end, we have 2b is less than or equal to nu p of b. Okay, so let's maybe put this in purple and let's compare the purple box and the blue underline, and notice they are contradictory. So we've reached this contradiction. But what exactly did we contradict? Well, we contradicted this ability right here to find a prime divisor of C that was bigger than or equal to 3. So that means there are no prime divisors of C that are bigger than or equal to 3, which means the only prime divisor of C is the number 2, which means we in fact have m equal to 2 to the b, whereas n is equal to 2 to the a. So let's take that information and we're ready to finish it off. So where are we so far? Well, we've shown that m and n are both powers of 2 and they're relatively prime powers of 2. Okay, so now let's plug that back into our equation over here. So what will we have? We'll have 2 to the a all raised m squared. So let's see, m squared will be 2 to the 2b, and we need this to be equal to m. Well, that's 2 to the b, and then we'll have n plus 2, so that's 2 to the a plus 2. So we've got something like that. And now let's simplify this a little bit. We'll have 2 to the a times 2 to the 2b equals 2 to the b times 2a plus 2. Okay, so that's where we're at. So now let's maybe take the log base 2 of both sides, and that'll leave us with a times 2 to the 2b equals 2a times b. Maybe we'll write it as b times 2 to the a plus 2 times b. Okay, well now let's explicitly point out something that we've implicitly assumed along the way, and that is that a and b are both bigger than or equal to 1. Because if any of them are equal to 0, that means m or n is equal to 2 to the 0, which is 1, and we covered that over here. But now that'll leave us with a times 2 to the 2b minus 1 equals b times 2 to the a minus 1 plus b. But now let's factor this right-hand side. We can factor a b out, and that'll leave us with 2 to the power of a minus 1 plus 1. Okay, now we're going to break this into a couple of cases. So let's look at case number 1. So case number 1 is a is equal to 1. And that's an important case because if a is equal to 1, then that means this object right here is equal to 2. So notice the left-hand side here is even, which means something over here is even. If a is bigger than 1, this term, this 2 to the a minus 1 plus 1 is odd, which means b must be even. So we're looking at the other case for that. Okay, so like I said, let's look at the case when a is equal to 1. But that's going to collapse everything to 2 to the 2b minus 1 equals 2 times b. Okay, but then we can divide by 2 again, and that'll leave us with 2 to the 2b minus 2 is equal to b. But that's an exponential versus polynomial equation, and we know that those will only have solutions exactly one place where the variable is very small. And in fact, it's like quote unquote easy to check that this has a single solution, which will be the case when b is equal to 1. So if a is equal to 1, then that implies that b also must be equal to 1. But that gives us our second solution. So we'll have m is equal to 2 and n is also equal to 2. Great. Which means we should move on to the next case. So the next case will be the case when a is bigger than 1. So let's write that down. We have a is bigger than 1. But notice if a is bigger than 1, then this term right here, 2 to the a plus 1 is odd. But the left-hand side, like we said before, is even, which tells us that b has to be even. So we have b is even. But now let's maybe use that and let's write b as 2 to some power which is large enough to take all of the evenness out. What should we call that? Maybe 2 to the x times y, where y is an odd number. Okay, so we factored all of the evenness out of b. Okay, so now let's plug that into our equation over here. So we have a times 2 to the, well, it's 2b minus 1. So let's see, that'll be something like this. 2 to the x plus 1 times y minus 1. And then that is equal to b, which is 2 to the x times y. Y is odd, and this is odd, so I'll just write y as an odd number. Okay, so we've got something like this going. But now let's notice the following. Notice that the power of 2 over here on the left-hand side is larger than the power of 2 on the right-hand side. We have 2 to the x plus 1 times y minus 1 is definitely strictly bigger than x. And that's just because that exponential really quickly outgrows that linear term. But then that means that the left-hand side has more even factors than the right-hand side. But that's impossible if we've got an equation, so that brings us to this contradiction. So we've contradicted the possibility of a being bigger than 1, which means a really had to be equal to 1, which led us to this solution over here. So in the end, we have two solutions, both of these being equal to 1, or both of them being equal to 2. And that's a good place to stop.